So topic for 1.3 is density. So this is the degree of consistency, and it has a measure, a quantity, using the Greek letter rho. Physics and engineers can represent density by calculating the mass over volume. And this picture is kind of a good representation. As the atomic structure of the object becomes more condensed, the more dense the object will become. Some objects float in water, they're less dense. Other objects sink, they're more dense. And that has to do with the arrangement of the particles for that object. And then you can kind of see that relationship based on the calculation, mass over volume. It's a very large mass over a very small volume. It's going to be a larger density. Therefore, more dense means it's going to sink. So other properties, physical and chemical change. Physical change is appearance change, visible change, maybe a color change. But the chemical composition is not different. Boiling water, still water. Melting things, cutting, bending, split, crack, whatever it may be. These are physical changes. A chemical change is when new matter is formed. Think about rust, burning something, decomposition through microbial activity. These are all changes that you can't get back once the change is made. So the difference here between endothermic, absorbing energy, and exothermic, releasing energy to the surroundings. You can think about ice in your hand. The ice itself isn't heating up. The ice is still the same temperature, but it is absorbing energy from any object you place it on. If you place it in your hand, it's going to absorb the warmth from your hand. If it's still an ice cube, it's still the same temperature. Exothermic is releasing energy. And so you can kind of see that in the picture, energy being released because of the chemical reaction. So lots of examples here of physical changes. Some with some good examples, but all physical changes are not changes to the molecular structure. Chemical changes, you are actually changing the molecular structure. You're changing the object, and most of the time you cannot get that object back. So a lot of examples there. So this phase change graph has been used a lot, and I like to use water because it's a known object that can go through all three states on Earth. So if you have frozen water, it's solid, and when you're moving from a solid to a liquid, like I said, you're holding it in your hand. It doesn't change temperature until it's melted. Once the ice is melted, then it can start to increase in temperature over 0 degrees. So you have this latent heat period, time where energy is going into breaking the bonds of the solid, creating the liquid water. And then it will increase slowly once energy is added until it reaches, right before it reaches 100 degrees Celsius. Then the energy added there's a latent period again. Energy added, once it breaks that bond and becomes boiling, then it can evaporate into gas. So a lot of these terms should be familiar. There are also instances where the solid will go straight to gas, skipping the liquid phase, or the gas will go directly to a solid. This takes a lot more energy, and there are some examples. You can think about sublimation. A solid that goes directly to a gas would be dry ice. Dry ice is a solid, and it evaporates straight into a gas. Deposition, a gas to a solid, could be ice forming on your windshield. That's a good example. And it may not rain overnight, but sometimes you might get ice on your windshield even though it didn't rain, and that's because the water vapor of the gas solidified on the surface of the windshield, becoming a solid and skipping the liquid state. So here's some more detailed explanation of the phase change terms. And here you have examples of various elements, the temperature for boiling point and the temperature for the melting point. Very, very high and very low temperatures compared to what takes place with water. Vaporization is the latent period where the molecular structure of liquid is changing. There is a latent heat period for moving from a solid to a liquid and from a liquid to a gas. But if it's called vaporization, you know it's going to a gas because it's becoming a vapor. That is the end of the notes. Quickly look at the schedule for today. Covering density. There's a warm-up, exit ticket, quiz, and the density lab. You will need some materials for the density lab, so look over that briefly before you begin class. You're going to need a couple of different materials, and I'll also post a video conducting this density lab. All right, have a great day.